Okay, now we are at 7.3, morphology and condition that trigger the SCC. Okay, so take note that SCC, when it fail without plastic deformation. So you learned about metals, right? And I think your lecturer showed you before the tensile graph of metals. So when you pull the metals will experience one region that called plastic deformation. However, when it comes to SCC, corrosion cracking mechanism, SCC do not need plastic deformation. You cannot see plastic deformation in SCC. So sometimes it might be mistaken for fracture or brittle material. You might see that maybe there's some brittle material happen. So instead, metals suffer SCC and normally they are ductile. So so just take note, sometimes SCC will happen when the metal is ductile. Ductile means you're able to pull it, but without the plastic deformation phase. Then when you talk about cracking, we talk about mechanism, there will be a direction. All right, there will be a direction of the movement of the crack. So just take note on that. The crack and growth is perpendicular to the maximum tensile stress. Okay, the crack is perpendicular to the tensile stress. What is tensile? Tensile is pulling in both ends. Compression, okay, going this way. Tensile, pulling both ends. So when you're pulling both ends, the crack will happen 90 degrees. Right? And without show visible corrosion product, there's no product. There's no like side effect like what you learned in the previous chapter. There's no oxide happen, right? There's no oxide, there's no carbonate happen. But in SCC, straight away it create crack. It create a canyon at that localized track, localized location. So if you look at the diagram previously, for example, I take this one. So as you can see, where is the SCC direction? You see the tensile at both ends, right? Pulling both ends. Where is the direction of the cracking? 90 degree. If you draw a line here and you draw a 90 degree, so the arrow show the direction of cracking. So that is the way you explain about SCC. Okay. So again, crack growth in perpendicular direction or 90 degree to the maximum stress and do not show any products. So from this diagram, from ABCD, you can see that this is the appearance of SCC. So A is at the intergranular phases. You go into the intergranular of the metals. Right, metals, you have a lot of shape, right? Crystal shape. So you go through the crystal and crystal side or granular. Go to the granular A. B, transgranular means it go through between. It go into the granular, right? Third, you have a delta river intergranular. This one is a bit serious already, okay? And again, it depends on type of the alloy or metal you have. So this one is more, you can see embrittlement happen, right? It's like a root of the tree already. So it go into, it's like a river delta kind of shape. So you have 3 possible case here. And you can see there's a label of tensile stress, sigma, tensile stress, and it go this way. It go deep. It go deep. Although you say, there's an angle here or what, but in general, if you look from the side, the cracking will start from the top until below. So the trend is going this way. Okay, the trend is going this way. The trend is going this way. although there are some intergranular activity there. Okay. So this is a schematic. So this is more on the microscopic observation, where they cut the material and then look under microscope. This one on the left is 115 micron, meaning this line, if you measure from this point to this point, this length is 115 micron. So if you take this length, if you take this length and you put on here, for example, here to here is about 115, right? So you use your ruler to measure, right? This length is 115, so you can see quite small. Then this one is a bit bigger. This one is not smaller. This is smaller, 50 micron. So 50 micron means here to here, right? So if you study in material and if your FYP is dealing with material and you have an observation under microscope, make sure you have a scale in your microscopic photo. Make sure you put the scale in your photo. If not, it's very hard for the reader to understand what is the size of the thing that you want to discuss. So these are the things. Okay, and the material that you're seeing here is stainless steels 316, right? Stainless steels exposed to seawater. B is intergranular crack, also stainless steel, but different stainless steel. 304. This is 304. This is 316. Okay, 316, 304. So you can see this one is more like a delta river that you see just now, right? It's more towards this delta river intergranular cracking. Okay, this one is more on either this one or this one. Okay. Okay. So morphology and condition of occurrence, you will follow 3 steps. Initialization, or the starting point. More technical word they call incubation. They start to give energy to the cracking. Incubation, you incubate the thing. Then you start, once you have enough energy, then you propagate the cracking. And once the propagate enough deep, as for example thickness of the material, then we will call it failure, right? Mechanical failure means the break off or fracture or breakdown of the material. So incubation or initialization, propagation, and final failure. So each one of these is, you can see this one picture SCC from the bottom of the pit. So this one is the one that you can see. Okay, so 3 steps, 3 steps of SCC: incubation or initiation, propagation, and final mechanism failure. Okay, now if you look at this chart here, it tells you the time to failure. Time to fail of SCC is the sum of crack initialization time and crack growth time. Meaning it combines the 3 processes. It combines initialization and propagation time together. Then once it reaches propagation deep enough, then it will fail. So on this graph, y-axis is the thickness of the material, or you can say as a penetration. Penetration means how deep it goes, right? Or we just on the penetration itself, you have your maximum thickness of your material. Let's say you have 10 mm thickness. So from 0 to 10 mm is here, for example. So y-axis is corrosion penetration. Normally, what is mean by corrosion penetration is we focus on the thickness of the material. Then the x-axis is the time. Is the time. So here we have point A and point B. We have two different metals here. Metal A and metal B. So metal A and metal B. So if you look at A, you have the time, initiate, propagate, and fail. B, initiate or incubation, propagate, fail. Okay. So then there's a dash line here. It is fall under pitting, right? Called under pitting. Pitting means there's a hole there, hole on the surface, pitting. All right. On this graph, label this one. This region is unstable propagation, right? You have the DB is this one. DA is this one. Do you have a critical thickness? D sub CR. Okay. Okay. So here is the critical. This is the critical thickness for material A. This is critical thickness for B. Okay. Okay. So one thing I want to highlight here is this TA and TB. This is end of service life. This is the time that we're interested when it comes to engineering application, right? This T over here. Each individual material have their own shelf life or end of service life. So this is important when you design something using different material, right? End of life, end of service life. So fracture toughness of metal A is lower than B. Fracture toughness of A is lower than B from the graph itself, right? Because B can stretch further. Okay, B can stretch further the propagation time under SCC. So B is you can say stronger than the B in terms of SCC. And then you can see the critical size for A is smaller than B. A here is smaller than B. So if you're given same operating environment and we have two types of material to choose, normally B will be the most favored material under the same operating condition. However, normally if you're able to handle that stress, I mean the material, B will cost more expensive than A. Normally it's like that. So normally A will be cheaper than B, but because of the function that B can do, it can handle more stress, more SCC stress. So B will be the most choice, and people will sell higher price for B, right? And again, SCC still need to go back to the Venn diagram. You need three elements. You need metal, you need stress, you need environment. So these three must come at the exact specific condition. Okay, and the rest you can read from the graph also. Conventional approach, let me give you all. Okay, So conventional approach for when you're studying about SCC, you identify the environment. So still remember the Venn diagram, you have three elements. You have metal, environment, and stress. So you identify the environment that might happen, that contribute to the SCC. Yeah? Then the experiment determination of the time of a failure using smooth specimen. So when you study material, especially come to corrosion engineering, of course this module don't have lab, right? So under material subject, you should able to see the method, the structure, metal structure under microscope, and from there you will see how good is the curing and so on. But this one under SCC, you define the environment that that you think might trigger the SCC. Then after that, you use a smooth specimen to conduct the experiment under tensile stress. Right, you pull the material, put the material in the, right, you set the material under tensile loading, then you see whether how long it takes to fail the products. Okay, there are some standard to test SCC. All right, later we look at all the standards. Right, so there are certain ways already. People already write out all the steps already. Let's say you want to have SCC tensile test, there's a specific steps you need to follow. So choose environment and then determine the time to fail. Then in the experiment, you determine the stress. You determine from the graph itself. From the graph itself, you will get the stress value from the tensile machine. You get the normal stress. Then you calculate the threshold stress. Threshold stress. Mean after this value, you have threshold and nominal, and also fatigue fail value. This one threshold is if below this threshold, this stress, the subject is safe. When every time after passing certain stress, you will see the graph going up. So for example, I go back to this graph, right? So during test, if you having the stress, we determine the time, right? So this is not the correct graph to show you, but on the tensile machine, when you test for SCC, you will see the tensile loading versus time, or tensile loading versus strain. From there, you can check the threshold from where the object start to behave strangely from the line. So how to determine this threshold stress, nominal stress? There is a standard there. Okay, there's a standard, ISO standard or ASTM standard. You need to follow. Okay, but this one fall under material science. Material science. We study corrosion engineering. We need to know how we determine SCC, and then the detail one, that one fall under material science. Right? Okay, the next one we look at a few technical parameter. Let me show you all. Okay, now we look at some calculation or some formula or some key indicator when we talk about SCC. The first one is stress intensity factor, capital Ki, stress intensity factor. So from the word itself, you can understand. I think you can understand. So intensity factor is a ratio of something, or is a scale factor of something. How strong is the stress? Another one is fracture toughness. Fracture toughness, K sub IC, means if you compare the symbol, right? stress intensity factor K sub I, fracture toughness K sub IC, meaning this one is, if you see K sub IC, is something deal with the critical value. Okay. So before you look at the calculation, in our understanding, stress at the tip increases when the tip radius lower. What does it mean? Okay, read again. Stress at the tip, the SCC diagram just now. The stress at the tip increases as the tip radius lower. You know about stress, right? The more sharp of your devices you press on a surface, the more stress you have, right? The stress point, right? So the sharp, maybe you cannot see, very small. So maybe I use this one. So if your tip, right, let's say this black color is the SCC hole. So if the tip is rounded like this, meaning less stress. If this tip is very sharp, you imagine this tip as a sharp triangular, then the stress will be very, very high if you have a sharp corner here. Okay, you mean by this one, So it link with the mechanical stress understanding or chapter. Okay, so stress at the tip link with the radius of the tip there. So you are given one calculation here. Stress field at the tip, so this one Ki or this one, intensity, this one, you focus on the tip, given you by beta sigma square root of pi a. So copy this one. Stress intensity factor Ki equal to beta sigma square root of pi a. Beta is constant value. Beta link with the geometry, right? So range is about 1 to 2, between 1 to 2 beta. So it can be 1.1, 1.5, 1.8, depend on the geometry. Sigma is a stress. And when you use sigma, it means tensile stress. Unless you see sigma, then the sub C compress. So normally for SCC, we look at tensile. A is the crack size. A is a crack size. If you see pi, it means that normally you will see round shape, right? If you see pi in the equation, normally you have a round shape or round curve or something. So stress intensity factor give you by this equation. So this is a general equation. There's some remark here. So if you have an unstable fracture propagation, especially for low ductility metal, low ductility metal means brittle object, right? Brittle object means, like, of course, metal you cannot like say like grass lah, but some metals you knock, you already break already, right? For those low ductility metals, you need to replace Ki. You need to be careful on the KIC, critical value, called fracture toughness. So this one you can use to calculate for the stress field at the tip, especially when it comes to low ductility. Then you need to be careful on the value that you calculate. Low ductility, they will have one critical value, KIC. Okay. Next, we look at another equation. Okay. Another key indicator called crack growth and K sub I SCC. So subcritical growth means once you initiate, you have three phases of the crack, right? Initiate or incubation, propagation, and fail, right? So you have three phases. During incubation, or we call it subcritical, or sometimes it can be propagation, right? So subcritical means it haven't failed, subcritical. Ki has value between the limit given by two parameters. One, you look at K sub I SCC. We call it it's a threshold or it's the check value that indicate the value of the stress-inducing factor below which crack cannot grow by SCC mechanism. Meaning there's a value called SICC. If you have a value below this value, below this KISCC, meaning SCC cannot happen. As long as this value is reached, then SCC might be happen. Okay, below this value, SCC, you can say cannot happen. Right? So as long as this value is reached or higher than this value, then we can say SCC might be happen. Right? Then another one is the fracture toughness, KIC. Yeah? KIC. So depend on two. During the subcritical growth, we look at two parameters, K sub I SCC. What is the function of this KISCC? Is to check whether SCC happened already or not. Okay, KISCC, this one, it gives you to check whether SCC happened or not. Okay, whether SCC already have propagated or not. Okay, all right. So another one is called KIC. KIC, this one is more on the fracture toughness. Take out that, right? So we have two. When we study about crack growth, we look at two parameters. KI you calculate, right? KI, just now we have one formula for K sub I. So from that value, you calculate. Then you compare with the standard material chart. It will give you one value called KISCC. This one done by lots of scientists already, right? So this value, you check with the value. If the value is below this KISCC, then SCC do not happen. All right, another one is KIC. KIC. If you reach this value, mean fracture happen. Right? Okay, another one. Okay, this graph. This graph tells you the relationship between the crack growth rate, dA over dt. Just now in the formula for the KI, the A represent the size of the crack, right? Just now, this formula. This A is the crack size. So when you calculate the rate of the crack size, what you do, you take this A divided by time, you get the rate of the crack growth. Okay. Crack growth rate, you take dA over dt. And another one is stress intensity factor that you calculate, Ki. So if you look at the graph, this graph, we use the log scale, log dA dt versus the value of your Ki that you calculate, right? Log dA dt versus Ki. Ki, you already studied about the formula just now. So on the graph itself, you see a loss of ABC 1, 2, 3 value of Ki, SCC, KIC. Right? So what does it mean? On the graph, before you start anything, identify the axis first. Log dA dt versus Ki. Then from the graph itself, this shape will be changing. This shape will be changing. But as long as the line start on the graph, the first point on the graph will be Ki SCC, because this one we study about SCC, right? So as long as the crack start to move, the crack start to happen, the value of Ki SCC registered on the graph, meaning the Ki value here give you one value here. This value is called Ki SCC, meaning value that below this value, there's no SCC happen, there's no cracking happen. When this value, Ki value, when this Ki value more than Ki SCC, then cracks start to happen. All right, if I use this chart now, so cracks start to happen, and the rate is increasing, increasing until one stage. You see the rate is constant. There's no more rate. Rate is constant here. All right, straight line until one phase the crack continue to enlarge, and then you have KIC. When you have no more data to collect means the object already break. So at the breaking point is your KIC. Yeah, so you look at the graph, you have log the rate of growth rate, the crack growth rate, log versus KI. KI you calculate with the formula just now. All right, so you conduct through experiment, you register. Once you observe there's a crack happen either by tensile test or material scope and all this. Once you observe there is something changes to the property of the material, and you register there's a crack happen, right? Either you can check through ultrasound and all this. So KISCC happen. Then at one point, there's no more propagation of crack. You don't observe any propagation. And then at one point, propagation continue and then break. Once the object break, you reach KIC. Okay. So this is a general understanding about the graph. Okay. Now we start look at the zone. Zone 1, 2, 3. Okay, zone 1, or we call it interval 1. The crack growth rate depends strongly on Ki. Here. Here is you can say it's a linear, but it starts to fade away as you reach the end of the fresh one. So here, zone 1 or interval 1, your dA dt or log dA dt is increasing with Ki, or you can see this one as y versus x. Y versus x. As your x increase, your y increase. Okay, as your x increase, your y increase. So it depends strongly with Ki. And the slope is very steep. The slope is very steep. So we can say the relationship is strong. Strongly dependent on something. In this case, Ki, your x, you increase a little bit of x, your y already a lot. So Ki influence your y. So number two here, when there's no growth of your crack, there are two possible scenarios. So you have curve A here. This is B, this is B, this is A. Curve A, the slip dissolution mechanism happen. Just now we talked about two mechanisms, right? Slip dissolution and there's a rupture, right? There are two mechanisms that we discussed just now. So curve A is due to the slip dissolution. The rest you can read. A is because of dissolution, slip dissolution mechanism. Okay, the rest you can read. Curve B here, curve B, you can say it's like a straight line here. It's because of hydrogen embrittlement mechanism, which is the second mechanism, or rupture mechanism. Or just now you can say as anodic process and cathodic process. So this one is under cathodic process. Hydrogen embrittlement happen, then it will go through B curve. Okay. Okay. Meaning the curve, the crack is because of hydrogen embrittlement. If the curve behave like this, if the curve after 1, it give you like a straight line and not curve like this, then most highly possible hydrogen embrittlement can happen. So this chapter or this section also help you to read graph when you go into the field, and the material scientists give you this data, log dA versus Ki. You know how to read, and you know how to communicate with the material scientist. Okay, so you read from this graph. If you see there's a almost straight line, then it fall under cathodic process or hydrogen embrittlement. If we follow along this straight line and then there's a curve, it's under the anodic process, which is the dissolution, slip dissolution mechanism. Okay. Then interval number 3 here is crack growth increase rapidly as Ki approach fracture Kc. So this one, as your Ki value reach Kc, you will see the object will fail at here. Okay, next we look at crack growth and strain rate. Crack growth and strain rate. So you can see the axis first, maximum load and strain rate. You have understand what is strain, right? Strain is a deformation of material compared to original size. So you have a few material here, square, star, and the circle, right? You have 3 material. So this is the effect of strain rate on SCC, occurrence on MgAl, magnesium alloy, magnesium aluminum alloy, in a 20 gram over liter chromite. You dip the standard steels, not standard steel. You dip the alloy into chromite solution, then you test the sample, right? Containing different amount of chloride. This one done in 1973. Okay, so as you can see, this one is 2.5 gram, 5 gram, and 35 gram. Okay. So they changed the chromite solution. So as you increase, as you 2.5, you see the blue, the circle here, the curve shift towards the left side of the graph if you increase the chromite solution. Okay, you shift towards the left hand side, meaning the loading reduce, the value reduce as you increase the chromite solution, right? Circle one is this line, 2.5 gram. As you increase to 5, you see the shape shifted a little bit to the left, and the value of your maximum load drop as you increase the chromite, and you increase to from 2.5 to 35 gram. From this curve, it shift further down to here, meaning that the sample strength drop significantly. From if you increase 2.5 to 3.5, you increase the chromite percentage. Okay, so again, it tells you that the SCC, still back to the Venn diagram, it need 3 elements to trigger SCC: metals, stress, and also environment. Okay, metal, stress, and environment. So if you given the stress, you given the environment, you given the metals, then you will see the effect of these 3 on SCC. Another graph here. This is more on material, or you've seen this one in your material science. Stress versus strain, very normal tensile graph. Stress versus strain in megapascal. So this one is the under authentic stainless steels. It did not give you what type of stainless steel, but published by Magnan, 1996. Right. So I give you a table for the stainless steel earlier, right, before the break. There's a table about authentic and another type of stainless steel, right? So ferritic and authentics in one of the table. So anyway, back to this graph here, you can see that this one containing nitrogen for different strain rate in the free corrosion and under cathodic protection in magnesium chloride boiling solution. So it compare 2 scenarios. You have a control sample. Control sample means without the corrosion and corrosion, right? So control sample free from corrosion, you have 2 line here. And what happens if you change the environment? So under magnesium chloride, you see that the curve actually go up a little bit. And your measurement, somehow it give you like higher stress value here. Okay. Another graph. This graph is a small fluctuation of the tensile load on intergranular SCC occurrence on CMN steel. Carbon Mn is, you need to check, CMN steels in carbonate bicarbonate solution, 82 degrees C, and under a certain voltage potential here. So you can see stress versus frequency. Stress versus frequency means there's some shocking happen. And it gives you a point here. Static means there's no shocking. Right, point is around here, and if you increase the frequency, the threshold, this is stress sub TH is a threshold. So the threshold increase, right, as you reduce the frequency. 10 negative 6 to 10 negative 3. 10 negative 6, 10 power 6 is 1 over 1060. Here is 1 over 1000. 0.001 and 0.00006. Hertz. Okay. This one is high frequency, low frequency. Okay. So high frequency, low frequency, all right. As you go into lower, slower frequency, the threshold actually increases. So it depends on material. So this is just a sample of results from on a CMN steel under a solution. Okay, we continue with test method in our next class. Okay. Okay, I think we stop here.